Madhav, there is something I want to ask you. You drew this picture. And yesterday we were talking about, in the previous video, we were talking about representational systems. I want to use this kind of picture to represent something, see if that works for you.
Yeah.
All right? Suppose I'm going to use this thing that you put there, this. And that's a human being. Any human being is represented like that.
Yeah.
So I have these two human beings. Okay? Let's say this is Zam and this is Zina.
Okay.
Okay? And suppose I do this. And I want to say that this arrow means that Zam is taller than Zina.
Okay.
So Zam I'm going to put a Z and Zina is going to put next. I could say Zina is taller than somebody else.
Yeah.
You know, you could do this. Zina is taller than, let's say, Hercules. So that would mean if Zam is taller than Zina and Zina is taller than Hercules, then it would imply that Zam is taller than Hercules.
Yeah.
So there is actually this that comes,
Yeah.
but you don't have to do that, right?
Yeah.
You don't have to say it.
Yeah.
It's logically follows that it should be so,
Yeah.
right?
Yeah.
Now here is the problem that I'm facing. Suppose you say that. Now let me use a different chalk too, because this means is taller than. That's what this arrow means. Now let me use a different arrow, or the same arrow actually. So this is our friend Zam, and this is our friend Zina, and this is our friend Hercules. But this time I mean likes. So Zam likes Zina, and Zina likes Hercules, but that doesn't mean
Zina likes.
yeah.
Zam
So
likes
this is
Hercules?
strange. I mean,
No.
this looks the same to me.
Yeah.
And why is this okay? That influence, whereas the other influence is not okay. That's weird, right?
Strange. So,
Huh? It's the same kind of stuff, same diagram.
so is it something to do with what the arrow represents, rather than the arrow itself?
The arrow represents is taller than, and this represents likes.
Yeah.
But two different ways of
Yeah.
So what's so special about this one? What is it that this one has that this one doesn't have? Actually, I'll give you another one like that. This like that. Suppose I say this means is older than. Okay. And if I do this, same thing. You get the same thing, right?
Yeah.
If Zam is older than Zina and Zina is older than Hercules, then that means.
Zam.
So this and this are the same,
Yeah.
right? In fact, it is not even is older than. I could also say is as tall as.
Yeah. Yeah.
So what is it
Different about this one?
Yeah.
Yeah. And let me try another example.
Huh.
How about Zam is the son or is the child of Zina? Zina is the child of Hercules. Does that mean Zam is the child of Hercules?
That's interesting. So you're saying Zam is the child of. Right. So these two are the same. They seem to have the same kind of property.
Yeah, the thing doesn't go all the way to B.
Yeah, you can't conclude from here that Zam is a child of. Yeah, right.
That would be a very strange family.
Yeah. Right. But if you say ancestor of,
Yeah.
that's different, right? So if you say is ancestor of,
Yeah. Yeah.
then if this guy is the ancestor of this guy is the ancestor of this, it
That
follows.
makes sense. Yeah.
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 So these two are different from those other guys.
Yeah.
This has been kind of puzzling me.
Yeah.
Is there some way of doing this in terms of, your mathematics? Is there?
In terms of
So say this is a different kind of relation. This is one kind of relation, and that is a different. And these relations have
So usually something like this is called transitivity when
Wait,
Sam,
let me write that down. This is spelling, right?
I'm very bad with spellings, but I think that it sounds right.
So you mean this one
Yeah.
is transitive?
It's transitive because any relationship here from here to here, here to here implies a relationship from the beginning to the end as well. So any path implies the relationship.
So that's a transitive relation.
Yeah.
Okay. So you can then generalize to say, in any relation which is transitive, this will be the case.
Yeah.
So that means this is not a transitive relation.
Yeah.
Okay. So you could categorize these relations in terms of their mathematical properties.
Yeah.
Okay. So the logic then would follow. And if all I have to do next time I look at a relation is ask the question, is it transitive? Then I know.
Yeah.
Okay. So is this, you wrote here graphs to mean this, right?
Yeah.
But this is not the kind of graph that you have, like, this is the x-axis and the y-axis and so on.
Yeah.
Statistics.
Yeah. This is not statistics. Here what we're doing is, but what a graph is in mathematics.
But this is mathematics?
No, that's statistics.
Statistics is not math?
No, it's slightly different.
Okay, all right.
So here, this is the graph from graph theory in mathematics.
Okay.
Which is that there are nodes, vertices. These things are called nodes, vertices. Where there are various other names, and this.
So you mean this thing that you put here is a node?
Is a node. So
it's also
Zena
called
is a node.
It's also called the vertex.
Okay. So for example, here Zena is a node.
Zena is a node. Okay.
Sorry, Zam is a node.
Yeah.
Zena is a node. This is an edge.
What is the edge?
The line which connects two nodes or vertices.
Okay. So this is an edge.
Yeah. I think there's some other names for it. I think it's called an arc.
Oh, okay. Arc. But this is different, right? This I put a curved line. This just.
Yeah. So this is an undirected edge, and this would be a directed edge.
Okay, because there is an arrow, it is directed.
Yeah.
But is there a difference between? Suppose you do this. Is there a difference between this and this? They're both directed, but this is curved.
Oh, there's no difference between those.
Oh, really?
Yeah.
So I could do this.
Yeah. That's perfectly
Same thing.
fine.
Okay.
All that matters is that there is an edge between.
So there's no difference between this and this.
No.
Okay. So the length of line doesn't matter. Remember we talked about this yesterday.
Yeah.
Okay. Shape doesn't matter. Length doesn't matter.
Yeah.
Unlike the ones that we had.
So this
yesterday.
is similar to we had mentioned this in the previous video where we talked about the maps of trains of within a city, trains within a city. They usually code adjacency of stations, but not the distance.
Okay, adjacency meaning these two are adjacent.
Yeah.
These two are adjacent, but these two are not adjacent. There is some node in between.
There's some node in between.
Okay.
Yeah.
Okay.
So those are nodes, and these are edges, and edges have two nodes, obviously.
Yes.
They have a start node and
starting point and end point.
Point. And vertices can have as many nodes coming. Nodes can have as many edges coming out.
Okay. So the picture that you drew yesterday about trains.
Yeah.
Was that sort of graph theory?
Yeah, that would be graph theory.
We're doing math now.
Yeah.
Oh, okay. I didn't know that. Okay. So this is called graph theory.
Yeah. This is just a representation of what a graph is. But so this is not graph theory. This is just a representation of a graph.
Oh, okay.
Within graphs.
Okay.
So once again, the distinction between what it's representing and the representation is an important thing to draw over here.
So what's the difference between drawing an arc like this with an arrow and arc like this without an arrow? What would be the difference?
So you could say that this this arrow is the equivalent of something like this.
It works in both.
It works in both ways. So that's what that means. So what it could mean is that so there is a relation. So there is a relationship between Zena and Zam. We don't know whether it's mother, father, uncle, aunt, but that works both directions. Right? That they are related.
They are related.
They are
but
related.
Not if Zina is the mother of.
No, not that.
Yeah.
But they are related.
They're related is all that it's saying.
Is the
not the direction of relation.
Not the direction. Yeah.
Okay. So, like for example, is as tall as.
Yeah.
It will be in both directions.
Is as tall as.
If like Zina is as tall as. No, Zam is as tall as Zina.
Yeah.
Then Zina is as tall as. So my arrow here is actually wrong. I mean, I shouldn't use an
arrow. It's not wrong, but there's no need to put an arrow, or you can put an arrow.
It can be.
You're losing out some information when you just put one arrow.
Yeah, but it's also like I should actually put both directions.
To get more information.
But if you're putting only one arrow, it is misleading.
Right? Yeah, it is.
Ah, I see. So a transitive relation has this arrow. Is that correct? No, I guess not.
So
what's the difference between things like this and things like this?
So here it just means that the relation there's some level of equality. There's a relationship in both directions. So, like for example, here is taller than Zam is taller than Zina. Zina is taller than Hercules, but that doesn't mean that Zina is taller than Zam. It doesn't mean that
it cannot be. In fact, if Zam is taller than Zina, then Zina cannot be
taller.
Whereas the other one, it has to be.
It has,
Oh, that's nice. So it's kind of like the same kind of logic. If it's a transitive relation, it spreads.
The same logic goes.
It is true in the reverse as well.
Yeah.
So is there a name for this kind of stuff? It works in both directions.
So it's just called undirected.
Okay. You mean this is undirected?
Yeah.
It works in both ways. Okay. So like it's like if it is true this way, it is true this way as well.
Yeah.
Kind of symmetry.
Yeah.
Type relate. Okay. All right. I'm going to erase all this stuff. Let's take some other examples.
Yeah.
There's. So I want to try this. I want to try this relation. So suppose two people are married. Let's say is the spouse of. Okay. So if I do this, that means that X is the spouse of Y, which of course also means that Y is the spouse of X.
Yeah.
Now, suppose I have children. Then I could say, can I put something here?
That seems like an odd thing to do.
So suppose I do this. And this thing is like a node.
Yeah.
But it has some,
yeah.
This means parents.
Yeah.
Nodes. Then I can do this now, right?
Yeah.
And you have M and N. What that means is that these two are the offspring, right?
Yeah.
So this means is the offspring of.
So another way to do the same thing without using that box is to do something like it's a little more.
Oh, I see. Okay. So this means that this is the parent of M.
Yeah.
And this. Okay, these are both parents of M and N.
Yeah.
Okay.
Why this might be a better. So in this case, this is a better representation.
Easy to see.
Easy to see. But in the case, say now Y marries Z. remarries and they have a kid. Now you'll have to, in this thing, you'll have to put a
another circle. Yeah, okay.
That's a little bit.
I see. So if you do that, then you can say Z and X have,
Yeah.
Right. O.
Yeah.
Okay. Now we can say that N and O are half
siblings.
Half siblings, half brother, half sister.
Yeah.
Okay, I see. So you could use this for something like a lineage, right? So if you say something like in this kind of tree, Yeah, in this kind of graph.
Yeah.
If you have an arrow coming from here, then you could say X is the parent of M, and if you have something like that, you know, let's say P is the parent of X,
Yeah.
and
But
so
you
on.
want to put an arrow.
Yeah, and so on. So you could say if you go on, this is the ancestor of M.
Yeah.
Okay.
Yeah.
So this is sort of ancestry lineage,
Yeah.
and you can represent that in terms of
Yeah. So one thing, do we actually need these arrows? Because when you draw something like this, usually you do draw a family tree or something like that with this. So it's kind of redundant, the arrow, because you know that this when there's a downward
the
movement,
direction. Okay.
the direction.
The top-down direction gives you the arrow, effect of the arrow,
Effect of the
notation.
arrow without having. So
Okay.
we were talking in the previous video about wastage.
Yeah.
And this seems like a little bit of waste to have to always add this arrow every
Right.
time. You might face certain problems later. So what if this person marries this person
Right.
in some
Yeah, but that'd be
interesting.
interesting to find out how
Yeah.
to represent
Yeah.
those things.
Yeah.
Okay. So you could actually represent ancestry, lineage, and so on in this fashion. You
Yeah.
could also represent family trees.
Yeah.
Family tree. Oh, you said this is graph.
Huh.
Family trees. Is it a graph? I mean, that I'm getting confused now. What is a tree and what's a?
So a tree is something like this, where it doesn't have to be directed, but
Yeah, that's a tree.
yeah.
So okay, that's whether it is curved or not doesn't matter, right?
Yeah, whether it's
you
curved
said
or not
the
doesn't-
length doesn't matter,
Length
shape doesn't matter.
Yeah.
So
So this is a tree where there's no cycle.
that's a tree.
Yeah. Yeah. That looks
Nice.
kind of like a Christmas tree.
So this is the same as that kind
Yeah.
of stuff. Okay,
Yeah.
right.
Yeah. But so notice here that this is not allowed.
Mm.
No, but in this in
Here, you know, it's
yeah,
so this is not a tree, is what you're
this is
saying.
not a tree. Yeah.
Okay. Wait, what this is? I've heard this word. Let
Yeah.
me check that with you. This is what they use. I looked it up on Wikipedia, and they call it directed acyclic graph.
Yeah.
And sometimes I think I've heard people using this DAG. So this is what in the Wikipedia, this is what they're saying. I need to erase this stuff now. So they said cycle is like this. If you can go like this, and like this, and like this, then you can come back to here,
Yeah.
right? That's a cycle.
Yeah.
But if you can do this, so you're not going back,
Yeah.
right?
Yeah.
And the arrow means that you can't go back,
Yeah.
right? Unless there is an arrow the other way. You can only go from here to here.
Yeah.
You cannot go from here to here.
Yeah.
So this, they were saying this is actually acyclic.
Yeah. This is acyclic because you can go from here. There's no circle you
Right.
can actually
So
take.
this is a cycle.
Yeah. But notice if you remove the direction,
Right, then it becomes,
then there's
Yes.
problems because then if you remove the arrow, now you
it
can
means
go
both directions.
Yeah.
Right, okay. So if you don't have an arrow here,
Yeah.
okay, then this is a cycle.
This
you can
is a
go
cycle,
back.
yeah.
Okay. So a tree should not have cycles.
Yeah.
So that means that this can be a tree.
Yeah.
Okay. But you could in principle disallow this also, right? You cannot say two nodes can't come to the same node downwards
Yeah.
like that.
Yeah.
Okay. So you can use all these things to figure out the kinds of trees or kinds of
Kind of
graphs
graph,
you're
yeah,
making. Huh. That's very useful to know. So it looks like, again, as we saw yesterday, what it is doesn't matter. You can represent all kinds of things. So if I just drew a picture here,
Yeah.
and I asked you, what does it represent? You don't know.
You
You
don't
will
know,
say it's
yeah.
just a graph.
Yeah.
You don't know whether it's family tree or
Yeah.
this could be airport connections.
Yeah.
It could be all kinds of things. It could be biological.
This would be very hard for it to be a family tree.
That is true. Okay, yeah. This could be a family tree, right? So you could, I guess.
Yeah.
Yeah, but you just can't go back.
Yeah.
Yeah. Okay. That's a, so this is a very interesting notion, something that doesn't allow cycles. Okay.
Yeah.
So can we think about some other interesting applications of this? I want to take something a little more complicated.
Okay.
Let's think for a moment.